In this lesson, we study the CRC-Pi filter used after a rectifier. We will follow the energy and ripple through both capacitors, derive the direct current and ripple frequency models, analyze one practical filter, and then design a filter to meet specified output voltage and ripple limits. By the end of the lesson, you should be able to explain the role of every component, calculate the relevant ripple frequency, form separate equivalent circuits for direct current and ripple, analyze an existing filter, and select practical component values for a new design. Keep the distinction between DC behavior and ripple behavior clear throughout. A rectifier output contains a desired direct current component and an unwanted alternating ripple component. A single reservoir capacitor reduces the main ripple, but sensitive low-current circuits may require cleaner supply voltage. The CRC-Pi filter adds a loaded low-pass section, so it reduces ripple further while avoiding an inductor. The circuit has two shunt capacitors separated by a series resistor. The input capacitor, C1, acts as a reservoir. The resistor opposes ripple current and isolates the two capacitors. The output capacitor, C2, bypasses most remaining ripple around the load, RL. This arrangement resembles the Greek letter pi. Near each rectified peak, C1 charges towards the peak voltage. Between peaks, the rectifier stops supplying current and C1 releases stored charge, producing a smaller sawtooth-like ripple. The remaining ripple reaches the RC2 section. At ripple frequency, C2 presents low reactance, so most ripple current returns through C2 instead of flowing through the load. The capacitor discharge interval depends on how often charging peaks occur. For a half-wave rectifier, one charging peak occurs per mains cycle, so the ripple frequency equals the mains frequency. For a full-wave or bridge rectifier, two charging peaks occur per cycle, so the ripple frequency is twice the mains frequency. Thus, 50 Hz becomes 100 Hz. Assume the load current is approximately constant between charging peaks. The charge removed from C1 is load current multiplied by the discharge time. The same charge equals capacitance multiplied by the voltage change. Approximating the discharge time as 1 over ripple frequency gives the peak-to-peak ripple across C1, load current divided by ripple frequency times C1. The first capacitor ripple is often approximated as a triangular waveform. The RMS value of a zero-mean triangular waveform equals its peak-to-peak value divided by 2√3. Substituting the earlier result gives the RMS ripple as load current divided by 2√3 ripple frequency, and C1. This relation is particularly useful when selecting C1. For direct current, ideal capacitors are open circuits. The only conducting path is through the series resistor and the load. Therefore, the output DC voltage follows the voltage divider relation. The load current is the voltage across C1 divided by the total series resistance. The resistor power is I sub L squared times R. This power determines the resistor rating. Now examine only the ripple component. At ripple frequency, C2 is a shunt impedance in parallel with the load. That parallel combination is ZP. Together with the series resistor, it forms a loaded voltage divider. Simplifying the divider magnitude gives the loaded attenuation expression. Notice that both the load ratio and the frequency-dependent capacitor term remain in the denominator. The RMS ripple at the output equals the ripple applied to the second section multiplied by the magnitude of its transfer function. The ripple factor is the output RMS ripple divided by the DC output voltage. It is dimensionless and is often expressed as a percentage. A smaller transfer magnitude and a smaller ripple factor both indicate cleaner output voltage. If the load resistance is much larger than the series resistor, and omega RC2 is much greater than 1, the loaded attenuation simplifies. The magnitude is approximately 1 divided by omega RC2. This approximation gives excellent physical insight, but the full loaded expression should be used for design whenever the resistor is not negligible compared with the load. Increasing the capacitor reduces ripple. Increasing the resistor also improves ripple isolation. However, that same resistor produces a load-dependent DC voltage drop, consumes power, and worsens voltage regulation as load current changes. Therefore, component selection is not simply a matter of maximizing every value. A useful design balances ripple, output voltage, heating, size, cost, and regulation. Consider a bridge rectifier supplied at 50 Hz. The voltage across C1 has an average value of 18 volts and 1.2 volts RMS ripple. The second section uses a 150 ohm resistor, a 220 microfarad capacitor, and a 1.5 kilo ohm load. We will calculate DC output, ripple factor, and resistor power. Add direct current, use the voltage divider relation. 18 volts multiplied by 1500 divided by 1650 gives 16.36 volts at the load. Dividing by the 1.5 kilo load gives 10.91 milliamperes. The resistor therefore causes about 1.64 volts of DC loss at this operating point. At 100 Hz, omega RC2 equals 20.73. The loading term, 1 plus R divided by RL, is 1.10. Substitution in the full loaded expression gives an attenuation magnitude of 0.0482. Multiplying by the input ripple gives 57.8 mV RMS at the output. The ripple factor is 57.8 mV divided by 16.36 volts, giving 0.353%. The resistor dissipates 17.9 milliwatts. A quarter-watt resistor therefore provides ample steady-state margin. The final output is approximately 16.36 volts DC with 57.8 mV RMS ripple. Now design a filter. A bridge rectifier on a 50 Hz supply must provide approximately 12 volts at 25 milliamperes. The average voltage across C1 is 15 volts. The first capacitor ripple must not exceed 1 volt RMS, and the final output ripple must not exceed 0.05 volts RMS. We will select the load, C1, R, and C2. The required load resistance is 12 volts divided by 25 milliamperes, or 480 ohms. Rearranging the RMS ripple relation gives the minimum value of C1. Substitution gives 72.2 microfarads. We select the next suitable standard value, 100 microfarads, which provides additional ripple margin. The resistor must drop 3 volts at 25 milliamperes. Ohm's law gives 120 ohms. Its nominal dissipation is 75 milliwatts. A quarter-watt rating gives practical steady-state margin, provided surge and ambient temperature conditions are also considered. This resistor value also fixes the loading term used when selecting C2. The second section may pass no more than 5% of the ripple across C1. Rearranging the loaded attenuation expression for C2 gives its minimum value. With 120 ohms, 480 ohms, and 100 Hz, the minimum is approximately 265 microfarads. Select the standard value of 330 microfarads. Verification uses the selected standard values. The loaded attenuation is 0.0401, so the output ripple is 40.1 mV RMS, below the 50 mV limit. The DC output is 12 volts, and resistor dissipation remains 75 milliwatts. The design therefore meets both DC and ripple specifications. A calculation is not the end of the design. Check capacitor voltage ratings against maximum no-load and surge voltage. Confirm the ripple current rating of C1 and the surge capability of the rectifier. Observe electrolytic polarity. Account for capacitance tolerance and aging by using the minimum expected capacitance. Place C2 close to the load to reduce wiring impedance. The pi filter gives stronger smoothing than a single capacitor and remains simple, inexpensive, and compact because it uses no inductor. Its disadvantages are DC voltage loss, poor load regulation, resistor heating, and potentially large electrolytic capacitors. It is therefore most suitable for low-current analog supplies, bias and preamplifier stages, detector circuits, and extra smoothing before a voltage regulator. C1 provides the main reservoir action. The resistor and C2 then form a loaded low-pass section that reduces the remaining ripple. At direct current, both capacitors are open circuits and the resistor causes a load-dependent voltage drop. At ripple frequency, C2 bypasses ripple around the load. A complete design checks ripple, output voltage, resistor power, capacitor ratings, tolerance, and practical surge conditions. Thank you.